And so let's see what you guys said. How many states did you think there was? With labels displayed. All right. Ooh. Hoo-hoo. Wow. That is quite the split vote. People are all over the place. We'll get you to revote, but I'll give you a couple hints first. First of all, 42 is the tempting answer because there's 42 squares. But is 42 the number of states? No. 42 would be the number of states if in Connect 4, exactly one of them had one piece, and that was the whole game. Which is actually, that is how we started the course, right? If you remember, the very first thing we did was snakes and ladders. If you have a track of length 42, what do you need to encode a state? Just where is your piece? So like very early on in the course, we were doing this kind of thing. But it's more than 42. And yeah, try to think which one it is closest to. Of course, none of them are exactly right. Some people, I think, had some good discussion about what's a legal state and what's not. Some states you can't get to in Connect 4 because gravity will do things. But I want you to just choose the closest possible option. Question mark? No, yeah, just choose the closest possible option. Okay, so I'll have you revote. Try and see if you can puzzle together which it is. This kind of exercise is really important because when you're going to write a computer program that plays Connect 4 or something, you gotta like, how are you gonna store the states, right? And knowing how big it is will help you make the right kind of choice. Okay, so I'll give you another 2 minutes to revote. I love how split this is. This is excellent. So hopefully you guys will have some good discussion here.
It's the closest one because I think there's far more illegal states than legal ones. Like if it's floating above, like there's a piece in the top row and no pieces below. That's all.
Given state, the number of legal moves from there is 7. Because you can only put the piece on top of the piece.
That even has there's another times what
You could just do like you could have like when we had the snakes and ladders thing, if you landed on like the 8, then you just
it's times 7.
you ended on state 8 with probability 0, and the probability just went elsewhere.
Yeah.
So you could I guess you could still construct the 3 to the 42 state space, and it's just like anytime you are in an illegal state, like go to a legal one.
Yeah, you just slide it down.
Yeah, but that line of thinking runs into a problem when one row reaches the top, so you don't have 7 slices per move. Yeah. So you can't keep on going with multiplying by 7. I did think about that. There's a lot of states. I think this means actually take that. The question is how all the states need to like all the future states actions are in a state.
Probably.
I think there have to be 7 actions available in every state. It's not important. Because what matters is the state itself.
Great question.
Okay, I think there's like 2 people who haven't answered yet. So if you're the last 2 people, get your answer in. Okay, maybe. Oh, okay. All right. I think everybody's answered now. Let's stop here, and let's see what you guys are saying. Okay. So this time, pretty clear consensus. People like 3 to the 42, and of course it's not perfectly correct, but that is also the one that I chose. Reveal answer. So 3 to the 42. Why is it 3 to the 42? Well, there are, essentially speaking, 3 choices for every single square. So there's 42 squares. It's not that every square is a state, but every square could be one of 3 things. It could either be empty, it could have player 1's piece, or it could have player 2's piece. And when you have many squares, they multiply. So you have 3 choices for the first square, 3 choices for the second square, and so on. So altogether, it's going to be 3 to the 42. Of course, lots of good discussion about how many are actually legal, right? Of course, you can't have empty spaces below spaces that are filled. So of the 3 to the 42, there's some fraction of them, maybe even a large fraction of them, that are not possible, but even if only like 1% of them are real, 3 to the 42 is going to be the sort of right answer. The thing about these like exponential numbers is that 3 to the 42 is so much bigger than 2 to the 42. Like, it's hard to understate how big they are. Actually, let's do some quick little calculator math. So 3 to the 42 is 10 to the 20. So this e to the 20 means it's approximately 10 to the 20. Let's write these down. So 3 to the 42, this is for Connect 4. Connect 4 is approximately 10 to the 20, whereas 2 to the 42, which is like, some lower number, is going to be dramatically lower. 2 to the 42 is only 10 to the 12. Okay, the 4 barely matters. So you could write it down if you want, but let's just say 10 to the 12. So, it's like 10 to the 8 times bigger. That's like almost 1 trillion times bigger. So there's definitely more than 1 in a trillion states are legal states. So it's going to be like 1% of the states. And so when you think about these geometric numbers that are so large, something like, oh, well, most of them are legal states or illegal states, it won't matter. The total size will still be approximately 3 to the 42. So that's the right answer here. Why am I talking about this? Who cares how many states there are? It doesn't matter. Everything we've done in the course, of course, still will work. Even if you have 3 to the 42 states, everything we've done, all the Q learning, all the things like that, everything will work. And actually, we've already done essentially all the tools you need in the course to like do anything you want in reinforcement learning. Everything we're going to do in these last 2 weeks are kind of like little hacks to help things, like fancy things to help things out. And so, like I said, in principle, theoretically, this is not a problem. Like, it will work. But does anyone know a practical issue with numbers that are this big? Yeah.
Combinatorial explosion?
Yeah, I mean, this is the combinatorial explosion. This is a combinatorially large number. Why is that a problem? Who cares? Okay, that's fine. It's a big number. Yeah.
It's going to take ages for your computer to calculate it.
Yes. Okay. So first problem, even not calculating it, this will not fit in your computer. If you tell your computer, I need 10 to the 20 numbers, please store in your memory 10 to the 20 integers, the computer will say, okay, well, you better like go rent a data center or something, then we can do it. But on like your dopey little laptop, this is already like beyond what you can do. So if you say like NumPy, please make me an array with 10 to the 20 entries, it will just explode and your computer will light on fire. So this is already a problem. But even if it could fit on our computer, the other thing that you said is that it would just take forever to learn about. And that is because whenever you play through a game, right, you're learning about some number of states. You're learning about however many states you saw in that game. How many states will you see in a typical game of Connect 4? Well, you'll see, at most, 42 states in the game, right? Because it starts empty. Every time you fill up one more, when they're all filled up, the game is over. So in one run of Connect 4, you're going to see at most 42 states per game. See at most 42 states per game. All right? So how many games will it take you until you have seen all the states, or like enough of the states that it matters? And again, this is all very like hand wavy. Like, of course, not all the states matter. Maybe there's some like weird states that like you never encounter in practice, but just the size gives you this idea that if you're only seeing 42 states a game and there's like 10 to the 20 states, then you're going to need essentially 10 to the 19 games. So if you do, like 1,000 games per second, then it'll only take you like, okay, let's do, this is a fun calculation. Okay, this is every good mathematician must know how to use Wolfram Alpha to impress their friends with things like this. Okay, so 10 to the 19 games. Okay, 10 to the power 19. Okay, here we go. 10 to the 19 games. And let's say you do 1,000 games per second. So that's games, and then I'll divide it by this many games per second. So how long do you think it'll take to do, if we're doing 1,000 games per second? Actually, let's do 100,000. You can simulate 100,000 games of Connect 4 every second. That's how long it'll take us. You guys think it'll be like years, tens of years, hundreds of years? Let's find out. Okay. 29 times since the beginning of the last glacial period. Yeah, it only takes 3 million years until you've sorted out the states. So the algorithms we've been doing, they will in principle work. It's just that they are way too slow for games that have combinatorial explosion. So things like Guess Who, where it's like, not Guess Who, Connect 4, where there's this 3 to the 42. The other popular games that are a little bit like this are chess. I wrote down these numbers for chess. So in chess, Connect 4 was a measly 10 to the 20 states. Chess is much more. Chess is 10 to the 40 states. And that is counting, someone did the math and counted only legal positions. If you count all the possible positions, it's like 10 to the 160. But legal ones, where there's like you don't have more pawns than you're supposed to have or something, is only 10 to the 40. Okay, that's not bad. But you might think this is twice as bad, sort of, as 10 to the 20, because 40 is twice as big as 20. But basically, if it took a million years before, now it takes 10 to the 20 times a million years. So now you're really screwed if you're going through a few states. If you can only go through a few states per second, like you really have no chance of visiting all the states. Okay, so chess is like this. The game of Go has 10 to the 170 states. So all of these things, you're just completely screwed. You can't even store an array with the number of states in your computer, let alone learn about it. Is like way too big for our methods. And really, our methods are fundamentally limited, that we're sort of like learning about each state. We're like, what is the value in this state? Okay, well, let's figure out the value in this state, figure out the value in that state. So we had this sort of like table, V of S, where S was a state. And it was sort of a table, so it's like S equals 0, S equals 1, S equals 2. And we were kind of learning the number for all the possible things separately. This method is way too slow to work for things like chess or Go or Connect 4. That's the first lesson of today, is that we got to find some way around this. Any questions or comments about that? All right, so what I want you to do is brainstorm. Has the whole course been a waste? Or is there something we can do to rescue it? And I think I came up with a word cloud, but brainstorm for a little bit. Let's try to think of what is a way around this. If you wanted to just focus on, say, Connect 4, how could you somehow do something clever so that A, it fits in your computer, and how would that help in terms of learning? Okay, so if you want a very concrete problem is, how would you make it fit in your computer at all? Okay, and then a little bit less concrete is, can we think of a way to improve the learning a little bit instead of just learning about one state at a time? Okay, so how did I phrase this? Instead of an array, how could we represent a function other than an array of values? So instead of thinking of an array with 1 entry, 2 entries, 3 entries, come up with a different way to think about it. That's what I want you to do. Okay, so go chat, brainstorm, and we'll have some discussion when you come back.
Literally a function of a whole bunch of variables.
Mainly the function where you plug the state in.
Yeah, exactly. And you're learning that function instead of
Oh, I see.
learning the
No, that's a good idea. I like
If you're
that.
learning that
Like-
function, isn't that just neural networks at that point?
Yeah.
Sure,
Yeah.
yes. It's better.
It's way better. They fit in a computer sometimes.
Yeah.
On your measly laptop.
Dopey laptop.
Dopey or Dopey. Yeah.
And then I think to run as the state,
this is
you
what-
have like, what's it called, like, to learning that we have like alpha
Yeah.
update.
That's the thing with machine learning as well. It's like momentum or something. It's like how fast you descend. If you're doing great, you descend. But at the start of the course, remember you said like you can use neural networks later in the course of learning. I feel like that's what this is. It's learning the value function as something like that, where it's a function of the, like you input for 1, 0, 1, or 2 for each.
Yeah.
That way.
Okay, but how would you learn your function? By doing, okay, so you're saying you nest a bunch of functions to create big functions.
I don't know about, I don't know if it's sort of modifying.
You don't have to know
I was gonna say, it seems like not our problem at the moment.
Only calculate the
Well, that wasn't the question.
How do we?
What is the expected number of moves?
So how do we do that? It doesn't
Another
work.
part of it is actually, given that we don't know anything about it, times four.
I guess you can try and figure out the value of the states that you have the options to go to using like Monte Carlo for reference learning and like learn as you go. Like try and figure it out as you're playing the game.
I mean, I'm assuming that we have a way to get the kind of function. Like obviously there are ways, and like in deep learning, yeah. Then I guess if there are two states that are like close to each other, in theory, if you're learning for one, then you should be sort of in the realm for the other. But then you're defining what closeness means, which also seems sketchy. Like two states might be one change away from connect four and just be completely opposite things.
Yeah.
Like, how do you know you're away from that?
That's what I don't know.
It's not working the way we expected. Do more.
17 minutes later.
Like, maybe not work.
Okay, I have 10 votes. There's like 40 seconds left. Put in whatever your ideas. I'm hearing some good discussion around. We'll definitely take it up as a class.
Yeah. It's always something. At least we figured it out. Yeah. 2 hours.
You spend 8.
Yeah.
Probably half an hour of that including for
Yeah. There's no people who spend that shit much time. Like,
why isn't it working? It was no lab 2 question.
We should like advance
And I want to read
transformations,
actual
like
dates
neural
until
networks
you're
at
like,
this point, like
well, what's your
neural networks themselves are like supposedly
I was
an
gonna say that,
evaluation
I think.
of functions.
Okay, time's almost up.
And so
Let's see what you said.
combinations like that.
Change my initial message.
Okay, let's look at the word cloud here and take a look. Will this show me the word cloud? Okay. Function, network, neighboring, neural. I guess a lot of people put in neural network. Let's see what people put in neural network. Okay. Neural networks. Yeah, so neural networks were mentioned in the first week of class, which are very hot and are related to like machine learning. People kind of think of them as synonymous. That is definitely one possible answer. Neural network is a very special example of the kind of answer I have in mind. And let's see if someone said the more general thing. Heuristic function, yeah, weights like a neural network. I like this one because it's the idea of weights. So what are weights? Why are they called weights? I mean, there's not something you lift. They're numbers, and you multiply them by things, and people think of those as the weights. So weights just means the numbers that you multiply by to get things. Another word for weights in this situation is parameters. Well, let's see, did anybody write parameters? Probably not. I think I would have seen it on the tree. Okay. Use indicators. This is also, surprisingly, the right idea as well. Use function approximation. So all of these are the right idea. We have the actual thing we want is actually a function. And we've been calling it a function this whole time. We've always used it as a table of values. That's what we said our function is. But we could write it as an actual function. And the smart thing to do is when you're representing a function on your computer is to use a parametrized function. What I call a parametrized function. So we're going to go away from a table of values or just a simple array. That's what we've been doing on every time we've done the value function or the Q function. In this course, it's always been an array of values. What is the value at 0? What is the value at 1? What is the value of 2? And we're going to move from that to parametrized functions. Parametrized functions. Okay. And so parametrized functions, they have some set of parameters, and the parameters are combined to give a function. Neural networks are definitely an example. We'll get to that in a second. But an even simpler example are linear combinations of things. So the simplest possible is the linear combination of parameters. So if the parameters appear linearly, then you add them up. I will give you an example. I think we did a hand vote, and everybody knows the rules of chess. Who knows chess? Like, you could play a game if you had to. Okay, everyone knows. So I'm going to tell you the value function in chess. Here's the value function, v chess. V chess. I'm gonna give you an example of a nice linear parametrized function for chess. And again, if I was gonna make this a table, table would be so big, it would be like no computer in the world could store a table for all the states in chess. But I can write down a very simple parametrized function. It only has like 5 parameters, and it's a linear combination to tell you the value. Okay, here it is. It's the you look at the number of pawns you have. Number of pawns you have. That is some feature, right? That depends on S. So in the state S, I can count up how many pawns you have. I'm going to multiply that by 1. 1. And then I'm going to count up the number of pawns my enemy has. Number of pawns the enemy has. Again, that depends on S, right? So in the state S, the enemy has some number of pawns. I'm going to do a -1. So I get a +1 every time I have a pawn and a -1 every time my enemy has a pawn. The next parameters are more exciting. I'm going to get +3 for the number of, I'll say minor pieces. Minor pieces are knights and bishops. Knights plus bishops. And I'm going to get -3 every time my enemy has one. Number of minor pieces, knights plus bishops. And then I'm going to do 5 points for rooks. Let's write it like this. My rooks. And then enemy rooks. Does anyone know how much a queen is worth?
8.
9. Okay. Number of queens. Number of queens. Number of my queens, number of enemy queens. And you might think it's silly, why would I do number of queens when there's only ever one queen? But actually, this is a very nice, if you use this value function and you put it into a computer, you can get a pretty reasonable playing chess program that can beat a child. It can't beat someone who's quite good at chess. When I was in high school, we had a project to make a computer chess program. And basically, this was my value function. And then it had some computer search stuff on top of that. So it would search the game tree and it would try a bunch of stuff. But this was my value function, and it worked quite well. So you can get pretty far with this. And it'll have all sorts of emergent behavior. Like one thing, because you get +9 points for the number of your queens, and you only get +1 points for the number of pawns, when you have the opportunity to promote your pawn into a queen, the value function will say, that's a great move. You should definitely do that. You get 8 more points, right? Because we'll lose our pawn, it'll disappear, but we will gain a queen. So it already knows all sorts of things like this. It knows what trades are good. It knows if I can trade off my bishop for my enemy rook, I should definitely do that, because I'll lose 3 points over here, but I'll get +5 points over here by the enemy losing their rook. So this already encodes a lot of knowledge in chess. And actually, where did these numbers 1, 1, 3, 3, 5, 5, 9 come from? They came from chess grandmasters who played tens of thousands of games and told us. They were like, when you trade, you should not trade a rook for a knight. A rook is better than a knight. So the knowledge is already incorporated into these parameters. The knowledge of the game of chess is already baked into these parameters. And you can imagine, if you were going to learn this, if there was some game you didn't know, you could set these to unknown numbers, some parameters, and you could try to learn them over time. So in reality, we're going to look at things that are like this. We're going to look at things like v of s for some parameters theta, and we're going to do the sum of the theta I. I think I called them theta j everywhere. Let's call them theta j to be accurate. And then we're going to do some basis function bj of s. And j goes from 1 to the number of parameters. So this is a parametrized value function. And this one's linear in the parameters. A linear parametrized value function. Okay, and the example you saw, it had the features. These things called bj, these are called the features. The features. And the features are counting something that we know is important to the position. So in chess, the features, the example I gave you, the features were the number of pawns, the number of knights and bishops, the number of rooks, the number of queens. Those were the features. And I had them both for me and for my enemy. And then I think I had, how many parameters did I have? 1, 2, 3, 4, 5, 6, 7, I had 8 parameters. 1, -1, 3, -3, 5, -5, 9, -9. And if you do the combination of adding up the coefficients, which are either 1, 3, 5, or 9, times the feature, which is the number of each type of piece, that is a perfectly good value function. And of course, it's not exactly right? It's not the actual exact value function like we've been talking about in the course. But the hope is that this very simple thing, it can parametrize and approximate the true value function. We hope that this is approximately the true value function v of s. I guess we called it star at some point. We stopped writing that. But v star of s. So this one would actually depend on everything in chess, 10 to the 160 states or whatever, 10 to the 40 states, some huge number. And we just hope that this is close enough that we make the right choices. And that's what we're doing. So we're replacing a table with a set of parametrized functions. And this is the simplest possible thing. Questions or comments about that example? Yeah.
Yeah, this is about the example. How would that handle, like, trying to actually do checkmate? Like, if all the pieces were
Yes.
just had a queen?
Right. Okay, so this value function, all it knows about is material. So it just knows about, and in fact, it doesn't even know about kings.
Yeah, that's what
Right.
I was thinking.
So it would be very easy to checkmate this program by sacrificing pieces to get a good attack, right? And then you would win. If you made this, it wouldn't actually play chess very well. You would have to layer on top of it some kind of search. So if you do this and then you do something like just try like 3 moves into the future and don't tell me the value now, tell me the value of 3 states into the future, 3 moves into the future, try all the possible moves, and then apply this. Then it will be pretty good. If you also tell it, by the way, if you're checkmated 3 moves from now, give it like -1,000,000. So I guess we should add on plus 1,000 times you win. You win minus 1,000 times enemy wins. Which seems silly because like this would never happen for a state, but if you add on search, then this kind of thing can be relevant. So yeah, if you want to make it actually be good at chess, you have to also add on thinking a few moves ahead. Yeah, that's a great point. Other questions or comments? Okay. Okay, so this is a linear parametrized function. A lot of people said neural networks. What are neural networks? Neural networks are, you take this kind of thing and you do it again. So a neural network is something like this, and it becomes nonlinear. I'm going to write it out like this. A neural network is another type of parameterized function, and you would do v of s theta, and it's going to be, how did I write it out? I wrote it out like this. So same kind of start, j equals 1 to m of theta j, and I called this theta j in layer 2. You'll see why there's a 2 there in a minute. And then times some function phi of j equals 1 to m1 plus m2, theta j1 of bj of s. So this is an example of a neural network. Basically, I took the linear combinations that I had before, this linear feature, I put them through some function phi. So here phi is a function from r to r to r. I put them through the function phi, and then I did another linear combination. So it's like linear combinations inside linear combinations, and this addition of this nonlinear function lets you represent more complicated functions and that kind of thing. So it really is like a more complicated version of this. There is a mysterious reason about the universe that people don't really understand, that neural networks are very good at approximating real-life functions quite well. And nobody really knows why that is. It's easy to write down. It seems to work. It fits in our computers pretty well. Yeah, nobody knows like why they work so well. I guess like people have done them, and they're like, look, it works here, it works there. But this idea of like, why does this work so well for our computers is kind of mysterious. Okay, I'm missing some, okay, this should be like J2, this should be J1, and this should be B theta J1, J2 or something. You can draw these as some kind of system like this, where you have the values B1 of S, B2 of S, dot, 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 up to Bm1 of S. These are kind of like the inputs. And then you feed them through some system, and you get the output after one neuron. That is exactly what is represented over here. So this thing is the sum of J1 is 1 to M1 f theta of J1 J2 of 1 times Bj of S. This is the thing in the brackets is kind of fed into a neuron in the second layer. So you think of the Bj's, the basis functions, as the inputs, and then you're doing some computation on them to get some value, and you do that a bunch of times with different weights. And then you take all of those values and you do another combination of them to get the final output, which is V of S theta. So there's like a cartoon version of the formula. If you're interested in neural networks, I highly recommend you go online and watch some of these nice series. 3 Blue, 1 Brown has a great series on neural networks. Let's write that down. So we won't do a ton of neural network stuff in this course. But of course, if you know neural networks, you can combine it with what we're doing to make very powerful representations for the value function and then be able to do things. That can be a lot more powerful than just the linear kind of stuff we're gonna focus on. And if you want to, for example, if you want to do that in your final project, I encourage you to do so. That's a very exciting thing you could try. Okay, so this is another example of a parametrized function. Now we're thinking about parametrized functions. We have a list of parameters, and if you're given the list of parameters, you can compute the value function v. Okay. Why is this helpful? I think I've said it a bunch of times already, but it's helpful because the number of parameters can be much less than the number of states. So it's helpful. Why helpful? Because number of parameters can be much less than number of states. So the chess example is a great one. The number of states in chess is like billions and billions, but the number of parameters in the thing I gave, which is not great at chess, but not terrible, was like 8. So that's a great example. And if you can learn a small number of parameters that can represent the value function well, then it saves you having to learn some huge, ridiculous number of states. That is one major advantage. So it can fit in the computer, fits in the computer, etc. Okay, there is one other, a little bit more subtle reason why this stuff is actually also better than the number of states thing. And that is because you can learn about, you can generalize lessons you learn in one state to a different state. So I'm going to say it allows learning generalization. Let's use chess as the example. So suppose you were trying to learn about chess, and something happened over here on the board, and you got checkmated. I don't know. You screwed up over here, and you got back ranked checkmated. If you were learning about the old way we did it, with every single state we would learn separately, then the only state you would learn for is not what is to do with this corner of the board, but the entire state includes things like, is the pawn here, or is the pawn here, or is the pawn there? So in the scenario we were doing before, learning about one state at a time, putting it in a table, you would only literally learn about this exact state. And then the next game you were playing, if the pawns were like this, exact same situation as before, but the pawns were like this, you would go, oh, that's a completely different state. I don't know anything about that state. I learned about this one. I saw that last game. This one, no idea, right? And of course, a human will look at that and go, yeah, but they're different, but they're almost the same. Like the stuff going on here is the same as the stuff going on there. And last game you got checkmated, so please watch out and like do something different, right? And our old way of doing it, learning about one state at a time, would see these as completely different things. This would be V of S1, and this would be V of S2, and they would just be like different things. They would have different values. And you would not be able to learn about this state until you got checkmated the same way as you did before, and then you're like, oh, okay, I guess we've got to learn about it. That was all before. Now we have these basis functions, and the basis functions can be the same for different parts. So maybe there's a purple basis function called like B upper left corner of the state. And even though S1 and S2 are two different states, maybe they have the same value of the basis function for the upper left corner. And that basis function appears inside the value function. So when we're learning about the value function, and we're going, oh, rats, we should have defended ourselves harder in this state, then when this state comes up, because we only see the basis function for the upper left corner, it'll be exactly the same, and our knowledge from this situation will transfer over to this situation. So through the fact that we're looking at these like shadows, these basis functions that only encode like a special, they're a map from a large state space down to R, that lets us generalize from one state to the other state in a helpful way. So hopefully that would help us, and we'd say, okay, these two states are different, but they have the same value for B, and therefore they're related, and whatever we learn from one should carry over to the other. So that's what I mean by it allows learning generalization. Okay, of course this is like a soft idea right now. It's not like a mathematical theorem, but it's an idea. Okay, let's put a little light bulb. And we would learn it. How would we learn it in our setup? We would put something about the coefficient in front here. So the coefficient that goes in front of this thing, if we lose, we're like, oh, we should have defended ourselves harder. Maybe we would increase that coefficient, and the next time it comes along, we're like, oh, the coefficient is quite large. We should defend ourselves in the corner, or something. You can imagine this kind of thing. Is that idea vaguely clear? It's a little half-baked, but I think it's an important idea to say why these things are useful. Okay, so that's what we want to do. And this is all very nice stuff. Okay, so we've taken our arrays and we've replaced them with parametrized functions, and we're very excited because these parametrized functions, they have less parameters, they can generalize, and they're neural networks, which are very cool. So we're excited. Problem, everything we've learned before was for the arrays. So the question, instead of the question, how do we learn the values of the function, that's what we were looking at before, now the question becomes, how do we learn good parameters? How do we learn good values of the parameters? And so a great example is in the chess example. How did I know that a queen was 9 and not 8? Right? It took many years of chess knowledge of many people playing chess to learn that it should be 9 and not 8. How are we going to make our program do this kind of thing? How is it going to learn the value of the parameters? And this is, again, I think this is a good one. I could just tell you the answer, but it's worth your time to brainstorm a little bit and think about. Imagine you were trying to learn good values of parameters. How would you do it? How do you find parameter values that do what you want them to do? Okay, and I will again open up a little brainstorming session here. How can we search for parameters that are good? So of all the possible ways we could set the parameters, how do we make sure to find good ones? And again, I'll give you a few minutes to think and discuss and brainstorm.
Because we're still trying to approximate the value function, but instead of using outputs, we're using parameters. But
No, we're trying to find an evaluation function, searching for parameters.
yeah, I guess though, then how do you know when changing parameters versus the output?
It's not what parameters, like what parameter values.
Yep.
The states.
How much we weigh that.
First word. About that. Because otherwise you're just like going through shit and you're I guess it works. Yeah.
Which means you're looking for specific. We should be talking like, we should be talking
I know people use
So we need
this
to
sort of
figure
stuff.
out the parameters
Parameters.
that may, let us evaluate each state. Right, so that doesn't have to be
Things like that.
like on an
Yeah.
outside level. So like how we have to do like display.
Yeah, so there's a minute left. I only have 5 answers, so put in your guesses. Again, we're just brainstorming. There are no wrong answers here. It's just fun to see what you come up with or what you already thought about, how you're thinking it connects to other things you've seen from other classes.
What you said is, so that you could optimize it with respect to some loss function. You can do like essentially multi-table to check what you're getting.
Yeah, that's what I would assume, is that you would create some sort of like data with simulations and you would check.
Yeah, which is what we were trying to do before.
That would be-
Okay, I guess people are quiet. Maybe I'll stop a few seconds early. And let's see what you wrote. The last few answers in. Okay, and, okay, parameters, games, Q learning, winning, losing, Monte Carlo, I'm seeing. Okay, let's go through these things and read them in order. Estimate somehow. Yes, exactly. I will say there is a kind of a difference of way of thinking about it. Of course, it's mathematically exactly the same. Sometimes when you think of parameter estimation, you're thinking of there are these true parameters out there in the universe, and if only I could estimate what they really are. And this comes up, for example, in stats class. If you have some population and you're like, I need to know the mean of the population. Well, the mean of the population is something in the universe, and we're just trying to estimate what it is. That is very kind of different to what we're doing, because we are not, there's not that there is some parameter out there that is the right answer. We're just trying to find something that like approximates like what is going on and plays well. Like a good example is in chess, there is no actual value for how much a queen is worth or how much a pawn is worth. This is all like a construct of our mind to simplify the complicated game of chess and make it easy for our children to play and like do things. Sometimes you should sacrifice a queen for a pawn, right? This will never do that because this is 9 and this is 1. So this is some kind of simplification. If you ask me what is the true value of what a queen is worth, there is no true value. It's just that in this setup, the value 9 does a little bit better than the value 8, right? So 9 is kind of the best possible value you could put here in some sense. But it's not that there's a true thing in the universe that we're finding. We're just trying to make a value function that approximates the true value function as best as we can. And that's a little bit of a slightly different point of view than you have in stats class where there's a true parameter that you're trying to estimate. There are no true parameters here. We're just trying to find the ones that work as best as we can. So that is one thing. I don't know what prompted me to say all this. Maybe this parameter estimation thing. Optimization, right? So we're going to optimize something. We want to find ones that work better or worse. But how do we do it? Okay, great. This is amazing. Run simulations and adjust parameters based on the outcome. So this is a great idea, and this is kind of the basis for what we're going to do. And you can imagine that, especially for things like policies, we have rewards. For a given set of parameters, you can play that leads to a value function. Let's write these down. So here is idea number 1. And this is the starting point of what we're going to do. So given some parameters, given some thetas, then you can calculate v of s theta, or more generally v of s a comma theta. So I'm using the semicolon to be like, here's the actual function, that's the input, and then it depends on these parameters. Sometimes people put the theta like as a subscript or something, but the point is, it's some function that inputs the state space and using the parameters comes up with the value function or the Q function. And we've seen that if you have a value function or Q function, you can run policies. You can make a policy based on that. make policy, and then you can try it and see how well you're doing, right? And you can either measure how well you're doing by is the value function like close to what you're getting, or you could just be say like, do you get a lot of reward? Like, is the reward high? Make policy, check rewards, and that would be Monte Carlo simulation or TD simulation, but some simulations. And so a great example is kind of what you're doing for the final project. You could say, I'm just gonna make a policy for V and Qs with some thetas. Given some thetas, I'm just gonna go to the casino 1,000 times, see how well I do. That's great, so we've checked how well it does. And then the next idea, let's see what they wrote. This is the real heart of the idea. Adjust the parameters based on the outcome. So what you could actually do is adjust them in some way and try to improve it. So this, so far, we have written, this is like policy evaluation. Okay, and we don't have a nice way to improve it yet, like we did in the previous context. We had a way of improving the V's and the Q's. Those were our TD updates or our Monte Carlo updates. The rule Q goes to Q plus the learning rate alpha times like V minus V new minus V old. That kind of thing was a nice update. We can't see directly how to do that, but if you have this evaluation, one very simple thing you can do is you could just try some like random perturbations of the thetas. And this is called an evolutionary algorithm. So idea number one, evolutionary algo. So you can instead of trying just one set of thetas, try 10 thetas, and then you can see which one does the best. And then you can kind of use that as your next starting point and make 9 more that are close to the one that did the best, and then make some more. So try many thetas, keep the best ones, add slight perturbations to them. Okay, and I'm going to draw a dopey cartoon of how this works after I answer this question. Yeah?
So when we're trying to determine which thetas created the best value functions,
Yeah.
can we also like do a human check to see which in the simulation, like what a human expert would say the value of the game is?
Yes, I suppose you could. In this course, we haven't really been dealing with like what human experts do, but of course you could incorporate that into your thing. So you could say like something like, if you are deciding to do something and we have this list of data of all the human moves that have ever been played, and you're doing something very different than what the humans are doing, that means you're bad. Like you could incorporate that in somehow. So you could say your reward, you get a +1 reward whenever you do whatever the human did, right? So because we are the authors of the reward function, we can incorporate some data set of human moves into our reward function and use that. So you could build that in somehow. Yeah. Yeah, so far in the course we haven't done that yet. Okay, so I'm gonna draw a dopey cartoon of this idea, because this idea is all words right now and like symbols. I'm gonna try to make it geometry by drawing a little thing that looks like this. Okay, you have to bear with me. What is the x-axis and the y-axis? On the x-axis is theta, and if theta was one number, one single parameter, then it really would be one axis. But actually, in reality, theta is like 10 numbers or like 100 numbers. So you just have to imagine that I've taken r to the 100 or r to the 10, and I kind of just think about it as one location. So moving theta around is like this. And on the y-axis, I'm going to draw how well are you doing? How good? How good? And for something like this, how good is actually perfectly well defined. So if for some value of theta, take it to the casino and see how well it does. If it gets more money on average, that is good. If it gets less money on average, then it's bad. So this could, for example, be the return, the total return. It could also be something like if you have a data set and you're like, I want it to match the human moves. I want it to play chess like a human. Is it playing the same moves as the human more often or less often? So as soon as you have a measure of how good, and for different values of theta, you can draw this kind of cartoon graph. And the point is that some values of theta are very good, and some values of theta are very bad. I do want to actually flip it. Instead of making how good versus theta value, I'm going to make the reverse. It's going to be how bad. So let me cross this out and say how bad. So this thing is sometimes called the loss curve. Loss curve. So a low value, that means low loss. That means we're doing quite well. So in our situation, we're talking about rewards. It is kind of naturally set up the other way, but you'll see in a second that this loss thing is actually going to be interesting. So I'm going to make a little axis here. Good is down, bad is up. If you've ever gone shopping for a new computer or like a new CPU, you'll see graphs of like comparing different CPUs. And some of the metrics, you want them to be higher, like number of instructions per second, you want that to be higher, but then it'll be like, how many seconds did it take to render an image? And then like lower is better. So you'll see these graphs comparing things where they'll have a little axis like higher is better, lower is better. In my graph, good is down, bad is up. Okay, why am I saying all this? I just want to make a cartoon of this evolutionary algorithm that we did before. So what did we do? We started with some value over here. This was our initial guess for theta. And we tried 10 things that were near that. So we said like here, and here, and here, and here. And by running it through this and doing many simulations, we can get an idea of which ones are good and which ones are bad. So we can learn, given the x value of these thetas, we can learn the y value. And then we can say which ones did the best. And we can keep the ones that did the best. We'll keep these two. Good. And we will throw away these ones. These ones over here. These were worse, so bad, throw away. And then we can take these two as a starting point, and we can, again, make random perturbations in all the directions that you can move theta, and we'll get some new points. Maybe they'll look like this. Here, and here, and here. And some of them, maybe will be quite good, and some of them will be quite bad. But again, we can keep the best ones. We'll say, now, in this next round, these ones were the best. But we'll keep those ones. And then we'll keep doing it again and again and again. And if you just sort of move around randomly, plus you also add in this thing of testing them and seeing which ones are the best and only keeping the best ones, then over time, you will slowly morph down this hill. And you will kind of eventually find yourself at some value here. So maybe eventually. So this is a cartoon picture of an evolutionary algorithm. It's called an evolutionary algorithm is because this is how people imagine evolution works. Right? Over many generations, natural selection is picking out the best possible ones, and then over time you kind of reach some optimal thing, the best situation. Is that picture clear, how things are moving? Yeah?
Is this like kind of a gradient descent?
This is not, that's what we're going to get to. This is not gradient descent. Yes, this is an evolutionary algorithm. Yeah, that's a very good prescient comment. Yeah?
So is it just different because it's just moving in random directions? It doesn't really have like a sense of where it's moving to?
Exactly.
Okay.
So in this evolutionary algorithm, and the thing that is quite hidden here is, remember, I drew theta as one direction. In reality, if there's 100 directions, then like there's many directions, you can think of like into the board or out of the board, that are like irrelevant. And you're wasting a lot of time. You're doing a bunch of simulations of like you're trying all these things in all these different directions, and a lot of the directions don't matter. So you're kind of testing all these possible directions. The higher the dimension of theta, the more directions you have to test, and kind of it will grind to a halt. If this is a 1,000-dimensional thing, if I want to test each direction, I have to try 1,000 things, right? If I just try 10 things at a time, it'll take me forever to sort of explore the space. But this is essentially the idea that we want to have a system for moving down the hill and improving what's going on. Okay, yeah?
So by the random process, it's sort of settling at that value. We're not telling it, oh, we want to go in the direction.
Right, exactly. Yeah. So in this, and I think this is the first idea. If we have a method to evaluate something, you can always do this. As long as you can evaluate how good something is, you can always improve it by testing it, evaluating it, and deleting the ones that are like bad and keeping the ones that are good, and then like do it again. And this is how nature like does it, right? This is how nature makes a giraffe with a really long neck that can get up to a tree, even though there's like no computing going on, right? Nature just has a really good system for testing the giraffes. It puts them out in the nature, and then it like kills the ones that like didn't do well, and then like eventually you get really long neck giraffes, which are good. Yeah, good is down. Okay. Okay. So I think this one, if you understand this one, the thing we're actually going to do, and it was mentioned already, is not this, but it's something called gradient descent, and it's basically this plus let's go down the hill. Okay. So this is like move around randomly, and we're deleting ones. But actually, in what we're doing, it's possible for us to compute the direction of the hill. So all of this is for the evolutionary algorithm, which is a great first idea of improving, but is inefficient because you have to try a lot of directions, and when theta is a high dimensional thing, that can be difficult. In some situations, not only are you able to evaluate things, but you're able to figure out which direction to move in. And in those situations, you can improve this by doing something called gradient descent. So I'll draw the same picture again, and I'll show you how it's different. Gradient descent, how the algorithm is different. Gradient descent. And you have to be very careful not to write gradient descent. Descent, like that looks completely wrong. That's like who's the like skunk guy in Pepe Le Pew? Gradient descent. Okay, Pepe Le Pew's cousin. Okay, I don't know. Someone look that up. Is that actually how you spell it? It looks wrong to me. Okay, it looks right. Okay, good. There is an effect when you're like close to the blackboard. Everything looks wrong, and you feel like a crazy person. Okay. So gradient descent. So in gradient descent, again, you start with some random guess. So just like we started with a random guess before. But in gradient descent, you have a method to figure out which ways are good and bad. So there is some method to figure out that the direction down is this. So this is the new ingredient. New ingredient is the gradient. The gradient. Okay. And if you know which way is downhill, you don't have to bother simulating thousands and thousands of different things that are all over the place and then like killing the bad ones and keeping the good ones. You just say, let's just move down the hill. So if you have some method to figure out which direction would be the direction to improve things, then you can move down. And you can get theta 0, and this one will be theta 1, and so on. And so we'll recalculate which way is downhill at every step. And so it can be much more efficient. If you have this extra ingredient of knowing which direction things are improving, then everything will be nice. And we can do that in our situation as long as we make sure that everything is differentiable. So this is some people call these differentiable programming. In our parametrized functions, we're going to make sure that everything is a differentiable function of the parameters. And actually, the very first one we did has a very nice derivative. The very first thing we said is it should be a linear combination of the thetas. What is the derivative? Well, it's the derivative of a linear function. Nothing could be simpler. It's the most simple derivative. And so we're going to see how to do this in 1 second. Okay. Let me see what else people wrote. Any questions about this? I'm going to go back to the thing, yeah.
How do we handle getting stuck in like local minima?
This is a fantastic question you should worry about. And actually, both algorithms have this problem. So the evolutionary algorithm could also get stuck in a local minimum. The evolutionary algorithm does have a mechanism to escape local minimums. Do you know what that would be? Yeah.
It might just like throw you onto the other side of the hill.
Yes, it's just by random chance, right? Maybe there's one generation where they all go up the hill by random chance, and then you're doing this good, better thing, and then they go down. Like, that's possible. So the evolutionary algorithm, because it has a little bit of noise, has a method to escape local minimums. As I wrote the gradient descent, it does not have a mechanism. But we can take what we learned from the evolutionary one, and we can incorporate that into our gradient one. You could do the gradient plus some noise, and then you will sort of escape local minima. And actually, we're going to find out when we actually find the gradient. We don't know the gradient exactly. We just know like approximately where the gradient is. So our method will have the randomness built into it already. So let's say this actually has a name. This is sometimes called stochastic gradient descent. And in stochastic gradient descent, you move, like on average, you move down the hill, but you don't move down the hill exactly. You do down the hill plus some noise. Either the noise can be added artificially by a human, or it can be because you don't have a perfect estimate for the gradient, you just have a rough idea of where it is. Either way, you could call that stochastic gradient descent. Yeah, was there another question?
I was just going to ask, well, this is kind of like the upside down metropolis algorithm, where it's trying to find a peak of whatever, but in this case, we're just going to find the valley.
Yeah. And again, it is, whether you go up or down, is if you think of it as a loss function, something you want to minimize, or if you think of it as a reward, it's something you want to maximize. And there's like mathematically no reason to prefer one over the other. One of them is a minus sign away from the other one. So it's not that one is better than the other. I will say in practice, almost everybody uses a loss function for this kind of thing, even though in reinforcement learning, people use rewards. And I did see a Twitter debate at one point where people were like, rewards are stupid, we should use losses. It's just like, do you think of giving your Roomba a cookie, or do you think of hitting it on the head? Like, it's your choice. All right. These are great. Any other questions? Yeah.
Is there any reason to use like gradient descent over some other algorithm? Like, is it like better? Is it
Yeah.
or does it converge faster?
This is great. I think that the real advantage of gradient descent, and the reason it, like basically, first of all, I will say everybody uses gradient descent almost exclusively. So in practice, there is some kind of reason people like it. I think the reason people like it is because it scales very well with the dimension of the input. So the evolutionary algorithm gets worse as the input gets bigger, but gradient descent kind of doesn't get much worse. And in some ways it gets better because there's this local minima thing is less of a problem. In high dimensions, it's very unlikely to have a true local minima. Typically what happens is you have, even if it's very local minima E, in a high dimension, there's one direction you can escape the local minima. So that's like a saddle point. And so in high dimensions, you end up with a lot of saddle points, and this gradient thing typically doesn't tend to get stuck. And so the gradient descent scales really well with the dimension. The amount of work you have to do is sort of linear in the dimension, whereas these ones are like super linear in the dimension, and that's why people like this. Basically the last 10 years has been people just scaled up the dimension more and more and more, and they're like, it's still working, and then it just got better and better, and like that's how things happen. I think that's why people like gradient descent, because it scales well with the dimension. I will say a lot of it is still mysterious. Like nobody knows if this is a super nonlinear thing. People don't have like a proof that it converges or something. They're just like, we ran it, and look, it is outputting Shakespeare. Like, great. That's where we're at. Yeah, great question. Anyone else? Okay, so we're going to learn this kind of gradient descent thing. We're going to learn how to improve slightly. And this actually fits in with the motto we've been doing the whole term with TD learning and Monte Carlo learning, which is you should think of TD learning and Monte Carlo learning as you have an estimate for the value function and you're doing a small update, right? You take the new knowledge you gain, you have a small update, you update your value for V. That's going to fit exactly into this gradient descent picture. And so in our situation, in this picture that we've seen many times, where we have policy evaluation and policy improvement in a loop that we've seen many times before. So this is the loop that we've been running many times. So in this one, you estimate V pi for some pi, and in this one, you update pi. This fits very well into our gradient descent picture, and we're going to see that all you have to do is when you're working with parameters is you just have to find the right way to make the policy improvement a single step of gradient descent. So this is what we're going to eventually get to, is we're going to just find out how do you incorporate this gradient descent thing into the improvement step. And instead of updating the value function V, you're going to update the parameters theta by just one little step in some gradient direction, and then you'll be able to do the loop forever and sort of improve slowly over time. So that's what we're going to get to. Okay, fantastic. So let's see, what else did people write? Because I stopped rather early. Okay, yeah. Yeah, okay, this is, so someone wrote minimize, build a cost function. That's another name for a loss function. So yeah, people have the right kind of ideas. Minimizing, gradient descent, somebody even wrote gradient descent. This person had it backwards, right? They said gradient ascent, that's when you go up the hill. And again, it's just up to you which way you put it. We're always going to do the loss function down, so we're going to do gradient descent. And this makes me more confident that I spelled it correctly. Okay, that's fantastic. All right, okay, so that's the plan. But I think the picture is important. Like, why are we doing this stuff? Why is there gradient descent all of a sudden? It's for all the reasons here. We want to get rid of thinking of the number of states, and we want to start thinking of the number of parameters. And gradient descent is operating on the parameters to try to update them to do something that we want. Questions or comments? Okay, and we're going to start with a baby problem. You know, I like to start with the simplest possible problem so we can learn and then move up. So we're not going to do this quite yet. We're going to start with an even simpler problem, which is, let's say, function approximation. Function approximation by values. Okay, so in this one, we're going to have some function, I'm going to call it f of x theta. And to keep things simple, let's make it a linear function to start. So it's sum of theta j times bj of x for some basis functions j, going from 1 to the number of parameters. And the simplest possible thing we're going to start with is we're going to make it theta 1 times x plus theta 0 times 1. So this is the basis function number 0 is the 1 function, and the basis function number 1 is the function x. And this is f of x theta. This should be familiar to you because this is a line. Okay, so we're going to do x in r, and this is the equation of a line. So theta 1 is actually the slope of the line, and theta 0 is actually the intercept of the line. And we're going to ask ourselves, what would it look like to do this gradient descent thing if we wanted to make it so that, can we make it so that f of xi of theta is approximately yi for some list of x's and y's, some given list of x1, y1, x2, y2, da 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 da. And I'll draw you a little cartoon of what this looks like. So suppose you have a little plane over here, and somebody comes along and they say, I'm thinking of these points. This is x1, y1, and this is x2, y2, and this is x3, y3. And they're like, please, can you come up with a slope and an intercept, and then draw the line with the slope and the intercept. So this would be f of x theta, which is theta 1x plus y. Can you find the value theta 1x plus theta 0? And they say, can you find the value of theta 1 and theta 0 so that this orange line of slope theta 1 and intercept theta 0 gets as close to the points x2, y2, x3, y3, and x1, y1 as possible? All right, and this, when you do this with gradient descent, you'll see there's going to be an update rule for the theta. So we're going to start with some value of theta. We're going to update it little by little, and it'll sort of settle itself down into the right spot. And if you draw the picture, it will look exactly like this kind of thing, where for every given value of theta, theta is going to be an R2 now, right? It's a slope and an intercept. And you'll see we'll find a minimum. And in this particular example, it's a very nice theorem. You can draw this whole shape, and it's a nice quadratic equation that has one definite minimum. By the way, does this look familiar to anybody from other courses? This is what they do in stats class. So in stats class, this is called linear regression. Of course, we don't need to know that it's linear regression. For us, we're thinking of just how do you update the parameters of some parameterized function to make it do what you want. And we'll see that the loss function we're going to use, the loss function. So the loss function, again, is this curve that tells you for a given value of theta, how good or bad are you doing? The loss function is going to be the sum of yi minus f of xi comma theta. And remember, we want that to be small, so how do we make sure it's small? We square it, and then we add it up over all the examples, 1 to the number of examples, and maybe let's even take the average. So that'll be the purple curve for given values of theta. It'll either be higher or lower, and we're going to see how do you minimize this by gradient descent. Okay, and we're going to do the details next time. I'll make a nice little notebook. We're going to do it in NumPy like we always do, and you'll see these graphs moving around and settling down in the exact right spot. If you've already seen it in stats class, that's very good, but probably you didn't do it with gradient descent in stats class. And we're really using this to learn what gradient descent is. So if you've seen it before in stats class, you'll tack on this new gradient descent thing, and then we're going to move on to using exactly the same step in our policy improvement. Okay, and that'll all be in the next few classes. All right, I'll be around for a while. If you have any questions about the lab or anything, please feel free to come ask. But otherwise, see you guys on Thursday.